Here's a quick proof of the Pythagorean theorem and then a couple of calculations. I said quick proof. We'll see if it's quick. It's a proof by picture here. I'm going to draw a right triangle. I'm going to draw a right triangle here. You can draw any right triangle. I'm drawing this one with side lengths 3 and 6 just to keep myself on the grid. I'm going to draw that same triangle again, although I'm going to put the 3 here and then the 6 going across here. I'll draw it a third time, 3 and 6, and a last time, 3 and 6. So labeling some sides here, if I call this A and this B, and the hypotenuse is C, the A was the same as this one, the B was the same as that one, likewise this is A and this is B, and A and B, and all those hypotenuses are C. The area of that that square, is it obvious that that's a square? Well, we know that the sum of the angles is 180 degrees, so the sum of these two angles is 90 degrees, but this angle is the same as that one, so the sum of those two angles is 90 degrees, which means that the one in here has got to be 90 degrees as well. This is 90 degrees, likewise that's 90, and this is 90, and that's 90, and we've got ourselves a square on the inside. The area of that square is length times width. C times C. Let me get this thing colored in. The area of that square is C squared. I'm going to do this in red, see if you can see it. C squared is the area. Okay. Now I'm going to draw another square which is exactly the same size as this big square. So I'm going to start here and go down. So that's 9 tall, and I guess in this case 9 wide. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll draw myself this square. I'm going to draw the triangle in again here. So 3, 6. So there's my A, B, and C. Right. This time though, I'm going to move some things around. I'm going to draw that same triangle right here. And then right here. Okay. So there's 4 triangles in that original picture. 1, 2, 3, and 4. And I want to say that I have triangle 1 and 2 drawn here. 1 and 2. And 3 and 4 I've moved down into like I took them and I moved them down into that corner. So this is the same as 3 and 4. The total area of the square here is the same as the total area of the square there. The 4 triangles here have the same area as the 4 triangles there. So the leftover area here should be the same as the leftover area there. Well, the leftover area on the right-hand side is 2 pieces. There's a little square here, and there's a big square, or medium-sized square maybe, here. Well, how big is each of those? I see a side length of B here and a side length of B there, so this area is B squared. Likewise, there's a side length of A here and a side length of A there, so this area is A squared. The total minus 4 triangles was A squared plus B squared. The total minus the same 4 triangles over here is C squared. So we must have that the area A squared plus the area B squared is the area C squared. Right. There's the proof by picture of the Pythagorean theorem. Right. So using that, and I'm sure you've done this before, but I just want to make sure that if you have a right triangle and you know two side lengths, you ought to be able to find the other one. So for instance, in this case, if this is 3 and 6, how long is that other side? Well, this other side happens to be the hypotenuse here. We'll call it C. 3 squared plus 6 squared has to equal C squared. So that's 9 plus 36 has to equal C squared. It tells me that C squared is 9 plus 36 is 45. And so C must be the square root of 45, whatever that is. Okay. You may be able to simplify that. 45 happens to be 9 times 5. So this could be 3 root 5, sorry, 3 root 5. But you don't have to. The square root of 45 is good enough, right? In a lot of situations. Be careful here with the Pythagorean theorem. A squared plus b squared is equal to c squared. It is not the case that a plus b is equal to c, right? It is not the case that that's true. You can't just take the square root of both sides. Well, you can take the square root of both sides. The question is, make sure you do it right. And in particular, the square root of a squared plus b squared is not a plus b. Be careful with that. So, one other example here, because sometimes what you know is a side length, let's say this is 4, and a hypotenuse, let's say this is 5, and you want to find this other side over here. I'll call it x for the sake of coming up with a random name for a variable. And you say, well, how do I find that? Well, a lot of people are very comfortable with squaring. So 4 squared plus x squared equals 5 squared, and you have to solve for x. So x squared is 25 minus 16. X squared is 9. X equals 3. Right. Now, as you get more used to this, you don't always have to start in this form. The way I see this is, if I've got the two small sides, I'm going to square them and add them to get the square of the big side. If I've got the big side and one of the small sides, then I'm going to square them and subtract them to get the other side. And I have to make sure I'm subtracting the big one squared minus the smaller one squared. So that'll be a positive number. And then I can take a square root. Right? Either way. Pythagorean theorem. If you know two sides of a right triangle, you know all three.